Good day everyone. Today I will be discussing the introduction of vibration and noise control as part of the course Me22088 Vibration and Noise Control. My name is Dr. C. Sendamarikannan. I am an associate professor in the Department of Mechanical Engineering at Sri Venkateswara College of Engineering. To begin with, let's define vibration. Vibrations are oscillation of a system about an equilibrium position. In simpler terms, it is the repetitive back and forth movement of an object around a central point. Imagine pushing a child on a swing. As the swing moves back and forth, it's oscillating around the central resting position. This is a form of vibration. In this slide, we see a graph representing a typical vibration. The horizontal axis represents time, while the vertical axis represents position of the vibrating objects. The wave-like pattern shows how the object moves above and below the equilibrium position over time. Each complete wave represents one cycle of vibration. Vibration is not just a concept we encounter in engineering textbooks. It is a common occurrence in our daily lives. For instance, when you ride in a car, the engine vibrations are transmitted through the chassis and can be felt as a humming sensation. Similarly, when you use a mobile phone, the vibration features alert you to the incoming call or messages. These everyday examples highlights how vibrations play a crucial role in various aspects of our life. By understanding the principles of vibration, we can improve the design and functionality of everyday devices and systems. Here are some common examples of vibration and their frequencies. Waves 1 to 3 Hz. The gentle undulating motion of ocean waves is a form of low frequency vibration. Washing machine. During the spin cycles, the vibrations can be generated at the rate of 10 to 15 Hz. Impact hammer. Impact hammer has a frequency range of 20 to 30 Hz, fall within this range. Grinder. Consistent vibration of an electric grinder operates at a frequency of 60 Hz. Electric cooling fan. Rapid oscillations of this cooling fan blades create vibration in the frequency range of 1 to 140 Hz. Understanding these examples help us grasp how different types of vibrations occur and the frequencies at which they operate, providing insights into their practical applications and effects. Vibrations can be both useful and harmful depending on the context and application. Useful vibrations. Compressor. Vibrations in compressors are harnessed to efficiently compress gases in various industrial applications. Testing. Controlled vibrations are used in testing equipment to simulate real-world conditions and ensure durability and reliability. Ultrasonic cleaning. High-frequency vibrations are used in ultrasonic cleaners to remove contaminants from delicate items without causing damages. Harmful vibrations. On the other hand, this is unwanted vibrations can produce noise which can be nuisance and impact the quality of life. And sometimes these excessive vibrations can lead to structural failures and destruction of equipments, machineries and buildings. Wear and fatigues also can be happen due to continuous unnecessary vibrations which can cause wear and tear on components, leading to fatigue and eventual failures. By studying vibrations, we can mitigate their harmful effects while optimizing their beneficial applications, leading to safer and more efficient systems. Now let's delve into a dramatic example of harmful vibration that had a significant impact on engineering practices like Tacoma Narrows Bridge collapse. This is a suspension bridge that spanned the Tacoma Narrow Strait of Puget, Washington, USA, on November 7, 1940, just 4 months after its completion. The bridge famously collapsed due to wind-induced vibrations. The bridge failure was caused by a phenomenon known as aeroelastic flutter. This occurs when the frequency of wind forces matched the natural frequency of the bridge, causing it to resonate. The resonance amplified the bridge oscillations, leading to increasingly larger and more violent movements. As the wind continued to blow at a steady speed, the bridge entered into a state of oscillation that it could not recover from. The amplitude of the vibrations grew until the bridge structure could no longer withstand the forces acting upon it. Eventually, the bridge tore itself and collapsed into the water below. This collapse of the Tacoma Narrows Bridge has given several key lessons. Importance of understanding resonance. The incident highlighted the critical need to understand and control resonance in engineering structures. Engineers learned that even a seemingly stable structure could fail if subjected to resonant frequencies. Then second, design improvements. The disaster led to significant advancements in bridge design, including better aerodynamics shaping and the incorporation of dampening mechanisms to reduce the effects of wind-induced vibrations. The third, multidisciplinary approach. The bridge collapse underscored the importance of a multidisciplinary approach in engineering, combining principles of aerodynamics, structural dynamics, and material science. The Tacoma Narrows Bridge collapse remains a classic case study in engineering education, demonstrating the potential consequences of not accounting for dynamic forces and resonance. It serves as a powerful reminder of the importance of studying vibration to prevent similar failures and improve the safety and reliability of structures. Let's see the importance of vibrations. Why we are studying this? Vibrations can lead to excessive deflections and failure on the machines and structures. To reduce it through proper design of these machines and mountings is very important. To utilize the vibration profitably in some consumer and industrial applications, yes, that is also possible. To improve the efficiency of certain machining like casting, forging and welding process, that is also possible. To stimulate the earthquakes for geological research and to conduct the studies in design of nuclear reactors, that is very much essential so that the nuclear reactors should not fail. Now in this slide we going to see the key aspects to understand about vibration. Amplitude. This is the maximum displacement from the equilibrium position. In the graph, the amplitude is represented by the peak and trough of the wave. Higher amplitude means the object is moving further from its resting position and indicating stronger vibrations. Frequency. This is the number of cycles per second measured in hertz. In the graph, you can count how many complete waves occur in a given time period to determine the frequency. Higher the frequency means the object is oscillating more quickly. Period. The period is the time it takes for one complete cycle of vibration. It is the reciprocal of the frequency. For example, if the frequency is 2 Hz, the period is half of its second per cycle. Hence, understanding these fundamentals of concepts is very much crucial because they apply to various real-world scenarios, from designing buildings, understanding the earthquakes, and to design machineries so that it can operate smoothly without any excessive wear and tear. By mastering the basics of vibrations, we can better predict and control behavior of systems, ensuring safety and efficiency in engineering applications. Key aspects is to be very important. Once again, I conclude that amplitude, frequency, cycle, and time period. Frequency, denoted in Hertz, is a key parameter in vibration analysis. It represents the number of cycles that occur in a second. In illustration, we observe two scenarios: a spring with a weight that oscillates at 1 Hz, meaning it completes 1 cycles per second. The same spring with smaller weight oscillates at 3 Hz, completing 3 cycles per second. This demonstrates that frequency is influenced by the mass of the object and stiffness of the spring. Lighter weight results in higher frequency vibrations because the system can move more quickly. Understanding these relationships helps engineers to design systems that can operate efficiently under various conditions. The characteristics of vibrations vary based on factors like spring stiffness, mass attached with it. In the illustration, a weaker spring results in a lower frequency as it is capable of restoring the object quickly to its equilibrium position. Conversely, a stronger spring increases the frequency as it can restore the object more swiftly. A heavier weight tends to lower the frequency because it requires more force and time to oscillate, while a lighter weight increases the frequency. These principles are essential in mechanical design, where engineers need to select the appropriate spring and weight to ensure the system operates as intended. Whether it's reducing vibrations in sensitive equipment or harnessing in industrial processes, understanding these characteristics is very much essential and fundamental. Resonance is a phenomenon that occurs when the frequency of an external force matches the natural frequency of a system, leading to large amplitude of vibrations. This can be both beneficial and harmful. Beneficial applications include musical instruments, certain type of sensors where resonance enhances the performance. However, resonance can also cause severe damages as seen in the bridge collapse. In this case, the wind-induced vibrations matched the bridge's natural frequency, leading to large oscillations and ultimately catastrophic failure. In the illustration, we can see the resonance point where the vibration and natural frequency align, resulting in a peak amplitude. Engineers must design systems to avoid destructive resonance by ensuring that the natural frequencies of structures and machines don't coincide with the frequencies of external forces.